Hello everyone, my name is Mark. Welcome to my MA261 Fall 2019 Final Exam Walkthrough. Before we start with the first question, I would like to share with you my approach to solve exam problems. First, I would like to identify the type of question by looking at the keywords presented in the question prompt. The reason why I do this is because on your exam, the order of questions will be shuffled. This means the first question is not going to be related to your earliest content, and your final question is not going to be related to the latest content. Once we identify the problem type, the second step I will show you are the solving steps, which are the simple steps that you can take to arrive to the right solution. These are usually any missing information and any key equations related to the problem. Because question type identification as well as the solving steps can be applicable to any type of question of the same type. And these are the two things that I want you to take away from my videos. Well, with that said, let's go ahead and start with the first question. The first question is, which of the following pairs of equations describes a pair of orthogonal planes? Okay? So this is an orthogonal plane problem, and it is from your chapter 13.5. So obviously, by inspecting the question prompt, the obvious giveaway is the word of orthogonal planes. Well, other types of hints of this in this equation is, well, if we looking at the answer choices, right, we have this and we have this, right? These are the equations of a plane. So the question type is obviously orthogonal planes. Orthogonal planes. And the keywords is obviously orthogonal planes, right? And then you have the plane equations, right? Okay, so now we know what type of question we're looking at. Let's go ahead and start with the solving steps. Well, the first thing that you need to do is first find the normal vectors of the planes which are n1 and n2. Okay? So let's start in this problem. There's no easy way of telling which one is the orthogonal planes. So we're just gonna have to start with the first answer choice, alpha. So in the answer choice alpha, the n1 equals to 3, 2, 1, right? We're just taking the coefficients of the planes in front of the components, in front of the variable components. And n2 is just going to be 1, 1, negative 5. Okay? So once we have those, the second thing we're going to do is we're going to use the property of orthogonal plane. What is the property? Well, if the planes are orthogonal, the dot product of the normal vectors equals to 0. Okay, orthogonal if n1 dotted with n2 equals to 0. So let's take this dot product. n1 dot n2 equals to 3, right? And equals to, I'm just gonna copy and paste right here. Right, so these two dot products, so that equals to 3 times 1 plus 2 times 1 plus 1 times negative 5. Right, the answer is obviously 0. So these are orthogonal planes. right? So that's, and then the answer choice is alpha. You don't need to look into other answer choices and test any of them, right? Because we now know the first answer is the correct one. So I'm gonna go ahead and label these in brown. So they are the things related to the question only, specifically. And then the solving steps, you can apply that to any type of questions of orthogonal, related to orthogonal planes. All right, the second question, on which of the following types of quadric surface does the following parameterized curve R lie? Okay, so this is a quadric surface identification problem, right? The reason how I know this is because by looking at the question prompt, right, we can see the quadric surfaces, the word quadric surface is showing up. And by looking at the answer choices again, right, we see a bunch of names of the quadric surfaces. So this is a quadric surface identification. So quad surf ID. I'm just simplifying things for you. Right, and the keywords here is just quadric surface. Right? And then the names of the quadric surfaces. So, but this question I consider is sort of an outlier to your regular quadric surface identification problem, right? Because there is no quadric surface equations, right? We only get an equation of the parameterized curve. So that's why it's an outlier. But it's not really difficult to solve once you see it through, right? So let's go ahead and examine the R of t. Especially, we're going to look at the x component and then the z component. So the x component equal to t cosine t. And then the z component equals to negative t sine, or negative sine t, and then cosine t, my bad. Okay? So let's go ahead and examine the sine and cosine first. So if you see two components with the sine and cosine, right, that just immediately tells you this has something to do with a circle, right? So sine and cosine, that just tells you something of a circle. Well, let's go ahead and examine the rest of the components, which is the t particularly, right? So what this t is doing in this parameterization is, well, the sine and cosine tells us we have something of a circle, right? So we have a circle, but the fact that you have a t, right, especially we're looking at the radius, right, r equals to x squared plus z squared in this case, that will just give us, t squared plus t squared sine squared t plus t squared cosine squared t, right? This is obviously just t, right? So r equals to t. As I increase my parameterization variable t, my radius increases. So this is not exactly a circle, but as we go around the circle, the radius of the circle increases, like that. Okay, so the t tells us that circle gets bigger, right? Well, let's go ahead and finally examine the component of 3t squared. Right, so y equals to 3t squared. Right, what is this? This is exactly a parabola, right? Right, this is a parabola. So we have something of a circle and then a parabola, right? So that tells us the parameterized curve lies on a quadric surfaces that has a characteristic of a circle as well as a parabola, right? by recalling the knowledge of a quadric surfaces, you can easily tell that this is a circular paraboloid. Well, does circular or elliptical paraboloid even matter? Well, it doesn't, right? Because the answer choices only ask you for a paraboloid. So the correct answer of the second question is D, paraboloid. Question number 3. Calculate the arc length of R from 0 to pi over 3. Right, so this is obviously an arc length problem. Right, so how do we know that? Well, again, the question choice is very obvious. This is an arc length problem. So the keywords is, again, arc length. Well, another hint that we can figure out is, well, we are given the position vector, right? The parameterized curve, R of t. Okay. So the solving steps of arc length problem. Oh, actually, this is your chapter 14.4, length of curve chapter. So the first solving step is to find r prime of t, which equals to dr dt. Right. So in this case, r of t, right? If you take the derivative. Right, so let me just go ahead and change colors. Right, this is the example specifically related to this example problem. That will give us 6 cosine 2t 0 negative 6 sine 2t. Okay, so once we find r prime of t, what we're going to do next is the second step: find the magnitude of that vector r prime of t. Right, so this will give you rx prime square plus ry prime square plus rz prime square. Right, so then put everything inside the square root. In this case, the magnitude of this r prime of t is pretty simple, right? I think everybody understand that r prime of t, the magnitude of that is just going to be 6. Well, finally, to find the length of curve for the arc length, right, we're going to plug in the equation, which is L equals to a to the b. Well, actually, we're going to identify the AB first. So I'm going to put it at step 0. So step 0, find r of t, right? Sometimes this is obvious, sometimes it's not. And t belongs to a and b, right? You need to find a and b first. So now we have r prime of t of the magnitude we just found. Right, this equation is also equivalent to the magnitude of your velocity vector, v of t. I'm going to label this in red because this is an equation that we're going to use very often, and the length of curve is just going to be, right, this is again example specific. L equals to 0 to pi over 3. 6 dt equals to 6t 0 3 pi over 3 equals to 2 pi. Right, so let's go ahead and take a look at the answer. The answer choice is B, bravo. And that's how you solve an arc length problem. Question number 4. Find the maximum rate of change of function at the point -2 and 1. Okay, so, right, this is not so obvious about what type of question it is, right? And that's what I think this strategy starts to become more obviously important. So this is a gradient of a function problem. So function gradient problem. Okay. So the key words here, right? So there's no mention of gradients or a gradient of the word, right? So how do I know this is a function gradient problem? Well, look at the keywords here. What does the maximum rate of change tell you about a function, right? So rate of change is always related to the gradient of a multivariable function, just like a derivative, right? Think of a gradient as your derivative in the multivariable world. Okay, so the keyword is rate of change. Okay, rate of change, and you also have, in other cases, you will have steepest, maximum, I'll just call the max, and the minimum, right? So, and also you have ascent and descent, right? These are all keywords related to the gradient of a function, okay? So now we know this is a gradient problem, so how are we going to do about finding the gradient, right? So the first row, the rate of change problem, right? So the first thing you do is always to find the gradient of a function, right? So del gradient of x, f equals to fx, fy, fz, right? So you basically just, so since we have the function of f equals to 7 minus x squared minus y squared to the 1/2 power, right? We want to rewrite that just for us to take the derivative a little bit better. So gradient of f is just going to be equal to, so use the power rule, 1/2 negative 7 minus x2 minus y2 squared, negative 1/2, right? And then we're going to also use the chain rule of when we take the derivative with respect to x, so you have also the negative 2x right here as well. And then we also have since this is a two variable function, right? I only have x and y, so it's just x component and y component. So the rest is going to be the same thing, but I'm just going to copy and paste right here. Instead of 2x, it's 2y. Okay, so that's your gradient. And we can simplify this a little bit by canceling out the 2 and the 1/2. 2, 1/2. All right, this will give us negative x square root of 7 minus x squared minus y squared. And then you have negative x, therefore you have a negative y on the y component. So you have negative x and negative y. This is our gradient. Well, we have the gradient now, so natural thing that we can do is to plug in a point. Plug in a point into gradient to get the maximum rate of change, or ROC, or this is the steepest ascent. Okay? So I'm going to make a special note right here. So 2.1. If we want the minimum rate of change or the steepest descent, okay? What we can do is just flip the sign of gradient of f at point. Okay? So in this case, we want the maximum rate of change, so no need to go into 2.1. So gradient of f at 2 and 1 equals to 2 over 7 minus 4 minus 1. And then we're going to just copy and this and duplicate over here. And then instead of 2, we have 1 because it's y. That just give us 2 root of 2 and then negative 1. Sorry, this is negative 1, not 1, negative 1. Yeah, just let me go ahead and let me, yep, that's correct. Okay, actually, never mind. This is negative 2 and then 1, right? Just to verify that, right? Negative 2 and 1. Negative 2 and 1, so we have negative 2, so that's positive 2, and then negative 1. So we have positive 2, root 2, and then negative 1, root 2. Okay? So this is a gradient of the direction. So this is a vector, right? Vector contains magnitude and the direction. So in this case, we want to find the maximum rate of change. Rate of change is a scalar, and this scalar corresponds to the magnitude of the gradient at the point. So in order to find the actual maximum rate of change, which is we're gonna do the final step, which is find the gradient of f at point. This is the max ROC at point. So in this case, we have the gradient of 2, 1, right? And then we have the magnitude, and this will equal to 4, right? 2 squared, right? And then that's a square root of 2 squared is just 2 plus negative 1 squared and 2, and square root of the whole thing. This will be 4 plus 1 over 2, that's 5 over 2. And then, well, do we have answer for 5 over 2? Not quite. So what we can do is we can rearrange this to be 10 over 2, and then root 10, root 2. Do we have an answer now? No, we actually don't. Give me 1 second. Oh, never mind. It's 10 to the 4, 10 and 4. So that's 10 to, my bad. So that is the correct answer, which is C, Charlie, right? So this is how, so this is the solving steps to find the maximum rate of change for a function. Question number 5. Find the equation of tangent plane to the surface at the point of 1, 2, 1. So I think everybody should be able to identify this is a tangent plane problem, right? I'll call them TG and T plane. Okay? But here's my question for you. Is this a tangent plane to an explicit surface or implicit surface? Well, in case you haven't figured it out, this is an implicit surface problem. Why? Because the equation that they gave us is implicit. Right, so quick example of explicit and implicit difference. So explicit is z equals to function of x, y. Right? So the z, the dependent variable, the output variable is excluded, right? It's clearly defined on the left-hand side of the equation. But when it's implicit, which is function of f, x, y, and z equals to a constant or 0, right? In this case, the x, y, z, right, the independent variable and the dependent variable are mixed up together, and you cannot, or it's going to be often impossible or difficult, if not impossible, to separate the dependent variable z. So in this case, this is obviously an implicit surface. Right? So the key word here, we have tangent plane, right? Itself, right? The word tangent plane itself, as well as the function f of x, y, z equals to a constant. Okay? So now we know this is a tangent plane for implicit surface. Okay? So how are we going to solve this question? All right, how are we going to actually solve this question? Well, this is an implicit surface problem. So the first thing we're going to do, which is to prepare for it, we're going to find the partial derivative. Oh, actually, before that, let's just go ahead and write down step 0. I identify f, x, y, z. So I usually equals 0. So I usually move everything to the left-hand side, so the right-hand side equals 0, so that I don't make any mistakes. So this is to prevent in case they write the variables on both sides of the equation. Let's say we have another x or y term over here. We want to prevent that. Let's just go ahead and standardize our definition of big F. Right? So everything is moved to the left-hand side. Right-hand side is 0. So in this case, this is pretty easy to find. X, y, z equals to x squared plus minus y squared plus z squared plus 2 equals to 0. All right, so just f, right? So now we have f. So and then the first thing we're going to do is also, you know what we added, we're going to identify the point as well. So P point of A, B, C, okay? So the point we have is A, B, C equals to 1, 2, 1, okay? And then the first step we're going to do is to find the partial derivative of x with respect to x, with respect to y, and with respect to z. So find fx, fy, fz. Okay, so in this case, the fx equals to 2x, fy equals to minus 2y, and then fz equals to 2z. All right. The second thing is we're going to do. We're going to plug in since we have the point available, we're going to evaluate these fx, fy, and fz at the point we're interested in. So evaluate fx, fy, fz at point. Okay, so fx at the current point of 1, 2, 1 will be fx will be 2, fy will be -4, fz will be 2. Okay, so now we can utilize the final step, which is using the equation of the tangent plane. Okay, so the tangent plane equation definition will be, I'm going to say fx at ABC, and then equals to 2, fy, same thing, just to standardize everything, just to avoid any confusions. Okay. So the equation of the plane will be defined as, for the implicit surface, is tangent plane. The tangent plane for implicit surface is defined as fx at ABC and then multiplied by x minus a, so the x component of the point of interest, plus, as you might have guessed, it's just fx, but everything replaced with respect to y, and then b, and then plus one more time for z. So z, f of z at ABC, and then z minus c equal to 0. Okay? So what we're gonna, for this particular problem, right, this part is just gonna be 2, right? So 2x minus a, what is a? A is 1, plus or minus negative 4 minus 4, y minus 2, plus 2 times z plus 1 equals 0. And once we separate them, so we're going to have 2x minus 4y plus 2z. Moving the constant to the other side, we're going to have negative 4. And this will give us x minus 2y plus z equals to negative 2. So we just simplified it a little bit. And then this will be the answer corresponding to choice echo, right? Choice E. And this is how you can find tangent plane for an implicit surface. Question number 6. Let function be as such, and then find the partial derivative with respect to x at 1, 1. Right? This question is pretty straightforward, right? I think everybody can easily figure out this is just a partial derivatives problem, right? So the key word is just symbols, right? Just any sort of symbols of partial derivatives, right? So symbols of partial derivatives. Okay. So I think everybody understands how to do a partial derivatives, right? So the solving steps is really just do it, right? This is a pretty famous slogan, so I'm not gonna mention this, but for copyright issues, but just do it, right? But in case people who are confused, let's go ahead and break it down as well, right? So first step is just you guys just gonna find the partial derivatives. So in this case, we want to find partial f, partial x, and this will just be, if we take this with respect to x, so we are going to find is, partial derivative with respect to e is just going to be e plus, and then we're using the chain rule, 3y minus 3, and then, we're actually going to use product rule here as well, because we also have a sine component as well. So in this case, we're going to keep the partial chain rule, so times 1, and then we're going to multiply this by sine of pi x y, right? And then we're going to add another part, which is now we're going to treat the e component as a constant, so we're gonna just copy and paste everything over here, and we're going to differentiate with respect to sine, the sine term, the trigonometric term. Right, so we're gonna take this, right, cosine of, right, sine becomes cosine pi x y again, chain rule, so we're gonna have pi y over here. All right, so this is your partial derivative, and then the second step is just plug in. Right, so in this case, partial f, partial x at 1, 1, evaluated at 1, 1 equals to e times e times sine of pi times 1, or we're going to ignore that, and then plus e cosine pi times pi, right? So how are we going to evaluate the sine and cosine? For people who are familiar with sine and cosine, right, just go ahead and evaluate that. But for me, I don't usually trust myself of quickly evaluating these sine and cosine. So I just do it in a very dumb way. Or my monkey brain just likes to draw this cross, right? So I know where pi is, right? Pi is 180 degrees, and then we're gonna mark a little point at 180 degrees, and then we're gonna say this is -1 and 0, right? The coordinate is x -1 and 0. So sine is always related to the y component, and then the cosine is always related to the x component, right? So in this case, we're going to have cosine of pi, that's just going to give us -1, and sine of pi, which is going to be 0. So this entire term drops out, right? So entire term drops out, and then we're going to have -e times pi. So, and this is our answer chart, and which is correct. Right, this is just really quick way to do partial derivatives, and hopefully you don't make any algebraic mistakes. Algebraic. Anyway, you get the idea. Don't make any mistakes. Question number 7. The temperature at the point x, y is given by the function t. Find the rate of change of the temperature with respect to time t at t equals to 2 along the path r of a moving particle. Okay? Well, what type of question is this, right? Well, this is for people who might not be able to see it obviously. This is a chain rule problem. Well, how do I know that? Well, let's take a closer look at the problem statement, right? So let's count how many variables do we have, right? So we have t, right, variable t, and then t is related to x and y, right? Well, and let's go ahead and take a look at the r of t, right? R of t is at the end of the day is x of t and y of t, right? So what you realize is x and y is also a function of the variable t. So I don't even know if I hope you understand where I'm getting at. This question has multiple layers of variables, right? So we have the upmost dependent variable t, and then we have the intermediate variable of x and y, and the x and y also depend on the independent variable t. So this is actually a chain rule problem. Right, it might not be easy to tell, but if you pay close attention to the keywords that the problem is providing, it's not too difficult to tell. Okay, so the chain rule, and then how do we know that? Is because we have dependent, I'll say a function of f or a function of t. Usually it's these two, but they are not limited to these two variables. Dependent, intermediate, right, in this case x, y, or even z if you want. And then we also have the finally the deep independent variable t and s. Usually it's these two. Okay, and sometimes they will also give you something called partial f, partial s, or partial f, partial t, right? So these are the things that you should be looking out for when identifying chain rule problems. So how are we going to actually solve the problem, right? So let's go ahead and start with the first step. What in my opinion, is always going to be identify, right? I'll call them this step 0. Identify the dependent intermediate, and independent variables. Okay, this is a very, very important step for you to solve these type of questions so that you can, it helps you to have a better understanding of the structure of these variables. So t is a function of x and y, right? So x is a function of t, y is a function of t, and then finally the independent variable is just t. Okay, and then the first step, what I would call, is to draw a tree. Okay, draw a tree. Okay, so in this case we have the utmost is the dependent variable t, and t can be decomposed into x and y, right? When x and y and then dependent on t. Okay? And the second step, what I would do is what I call follow the tree from top to bottom. Right, I call them from the dependent variable to the independent variable. Okay, so let's go and trace that down. So we have, right, so we go from t to the x, and then x to the y, and then to the t. Right, so let's do it. This is a very simple example. But what if we have a function of f to function of x, y, z, and then x and y, z depend on t and s, and then t and s. Right. So what if I want to find partial f or partial s? Right. So we're gonna do the same thing. We're just gonna trace them down. Right. So from the top of the tree to, this is slight mistakes, this is y. So from the top, trace down from x to s, from y to s, and then from z to s. So this gives you, so once we do this, what we will be able to find is what we'll be able to do is to write down the partial derivative equation really easily. Okay, so that means we can write down, so the step 3, I'm going to go ahead and delete this for an example. Right, so we're going to separate this as a separate example. So step 3 is write down the chain rule equation following the tree order. Following the tree. What do you mean by that, right? So let's go ahead and go back to return to our example. Right, we traced from t to the top to x and to t. So what you're going to do is we're gonna have partial t equal to partial t partial x, right? So we went from t to x, and then we from x to t, right? So we're gonna write down dx dt, right? And we're gonna do the same for the other branch, which is from t to y and from y to t. So I'm gonna add a plus at the middle, right? So partial t partial y, and then times dy dt, and this is your chain rule equation by following the tree. Okay, so now we're just gonna go ahead and find the corresponding components inside this big equation. So step 4, find each term involved in the equation. So in this case, we have, I call them, we have the partial t, partial x, and then as well as partial t or partial x. This will just give us, we can just take the derivative of the original function. I'm gonna go ahead and copy it down. X y equals to x cubed y. We spent a lot of preparation just to get this point. Oops, a little bit of mistake right there. Gonna copy this and put it down here. All right, t of x is this, t of x y is this, and then partial t, partial x is gonna be 3x squared y. But we're not done yet. We want to express this actually in terms of the independent variable. So how are we going to do that? Well, if we go back to our r of t again is x of t, y of t. Right? So in this case, we equal to t and t squared. Okay, so every time you see an x, we replace it with t. Every time you see a y, we replace it with t squared. So what we're going to get is 3t squared times t squared. And then we can do the same thing for partial t, partial y. Let me just make this a little bit more compact to save some space. Partial t, partial y equals to, what we're going to get is x cubed. This will equals to t to the cubic. Right? So this is a partial t, partial y, and then partial t, partial x. And then we're going to focus on these two parts. So dx dt, let me just put it in a new line just to make it more clear. Dx dt equals to dx dt, so we're going to have 1 second, right? So x of t, let me just create a new line right here. So based on this equation, right, we're gonna find, which is x of t equals to t, y of t equals to t squared. So dx dt is just 1. dy dt is just gonna be 2t. Okay? Therefore, the small t is just gonna be let me gonna simplify this a little bit further. That's gonna be 3t to the fourth. Right, so in this case, we're gonna partial t, partial x. That's gonna be 3t to the fourth times 1 plus t to the cubic. That's originated from the partial t, partial y. And then we're gonna multiply this with dy dt, which is right here, and that is gonna be 2t. This will give us 5t to the fourth. And then we're going to evaluate, we're going to find the final step, which is plug in the value of independent variable. So in our case, the small t at t equals to 2 equals to 5 times 2 to the fourth, that's 16. 16 times 5, that's 80. And then that should be the correct answer. Echo. Okay? This is a little bit longer question, right? But I hope the preparation, drawing the tree, and then following the tree to arrive to your chain rule equation, and then and then the rest is just finding the components inside the chain rule equation, and then finally plug in a point, right? And this is how you can solve a chain rule question. Question number 8, consider the function this on R2, then the function, right, it gives you a few options to choose. So what type of question is this, right? Well, first of all, by looking at the answer choices, we can realize this is sort of extrema problem. But that's not enough, because we have 3 different types of extrema problem. Well, let me detail it to you. All right, so first of all is local extrema. And we also have absolute extrema. And then finally, we also have a quantum multiplier problem. Well, what's the difference between these three types of extrema problems? Well, first of all, the local extrema is the only extrema problem that does not have bound constraints. No bound constraints. Okay? For the absolute extrema problem is we do have we have bound constraints, and then we need to find them. We need to find bound constraints, both extrema exist, could exist. How about could exist? On the bounds or inside bounds, right? And then the difference between finding the solution for local extrema, absolute extrema is this one is we're going to use second derivative test. So SDT, second derivative test, and absolute extrema we're only going to need to use first derivative test. I'm not going to cover this in detail because it would be spending us too much time for diversion. And finally, the quantum multiplier is extrema, finding the extrema on the constraints, right? On the constraints. Sorry, not the constraints, on the bounds only. Okay? So by looking at this problem, the key giveaway is this little thing, R2. Okay? So R2, that means we have no, R2 means we have no bound constraints, right? The variable of x, y could exist for the entire real number 9. So this is a local extrema problem. And local extrema problem is your not 15, it's 15.7.1, chapter 15.7.1. Local extrema problem. Okay? And the keywords is just well, let's say if you have a local extrema, right? So local extrema and no bounds, right? In this case, it's r squared. Okay. So how do we solve this type of problem? Well, first thing we're going to do is find partial derivative of f with respect to x and with respect to y. fx, fy. In this case, fx equals to x cubed plus y right? So we have the function, we just take the partial derivative with respect to x, we get x cubed plus y, fy equals to x plus y squared. Oh, not y squared, it's y cubed. Okay? And then we're going to find the critical points. Find critical point CPs where fx equals to fy equals to 0, or fx or fy does not exist, D and E. Okay, so these are the two cases. Right, in our example, we can set fx equals to x3 plus y, x cubed plus y equals to 0. That gives us y equals to x negative x cubic. That means, and then we can sub this y into our fy. So let me just set this equation number 1. Sub 1 into fy, and then we're going to get fy equals to x plus x minus x9 equals to 0. I mean, do you really have to do this? Not exactly, because you can really tell that from this equation, right? So in this case, the only 3 points where the function of the left equals the function of the right is going to be x equals to 0, right? 0, 0, right? We also have, oh, never mind. Disregard what it just says, right? We're still gonna proceed the substitution method. We're gonna still proceed the substitution method. We're gonna arrive this equation. We're gonna arrive at x equals to 0, x equals to 1, x equals to negative 1. Okay? So if we substitute 1 in here, 1 minus 1 equals to 0. Right? Negative 1 minus negative 1 is 0. And then 0 minus 0 is still 0. Right? So we have 3 x value candidates. And then we're going to substitute these x values back into the equation 1, right? Then, since y equals to negative x cubed, then therefore if x equals to 0, y equals to 0. If x equals to 1, y equals to negative 1. If x equals to negative 1, y equals to 1. So therefore, we have 3 candidate points, which are the critical points. Therefore, critical points are 0, 0, 1, negative 1, negative 1, 1. Okay? So now we have the critical points. What else we need to do is, step 3, we're going to find the second partial derivatives, which are fxx, fyy, fxy. So in many cases, you can find fyx, which should be the equivalent of fxy should be equal to fyx. But we're just gonna focus on fxy here. So what we're gonna get is, so since we have fx and fy over here, that means our fxx going to equal to 3x squared, fyy equals to 3y squared, fxy is going to be 1. Okay? The fourth step is, so now we have enough information to calculate or find the something called discriminant. Okay? Discriminant, which is d of x, y equal to 1 second, fx x fy y minus fxy squared. And in this case, we will have, this is a very important equation for us. I'm going to label it in red. And in our case, we're going to have 3, so determinant of x, y equal to 3x squared, which we just obtained from over here, and then times 3y squared minus 1 squared, right? So 1 squared. That just equals to 9x squared y squared minus 1. Okay? Step 5, we're just going to use the second derivative test for two variables, which is based on the discriminant. So, step 5, second derivative test. For two variables. Okay? So first case, if discriminant at point AB is greater than 0, extrema exists. Okay? But we're not done yet, so because if fxx at AB is greater than 0, this means a local minimum. If this thing is smaller than 0, that means it's a local maximum. I think of this relationship as the concavity of in your 1D variable case, right? So let's say if we have a concave up function right here, right? The concavity is positive, it's concave up. That means we have local minimum right here, right? So positive concavity greater than 0, sort of the similar relationship, and it's backwards for the local maximum. Okay? And then if this discriminant is equal to 0, that means f at AB is a saddle point. Or AB is a saddle point, not FAB. AB is a saddle point. It's neither local max or min. Okay? If this thing is smaller than 0, that means the second derivative test is inconclusive. Inconclusive. Okay? So, in our case, if we test our point at 0, 0, let me just go ahead and copy these CP down, right? Oh, forgot to mention, we're going to test these at CP. Okay, at CPs. We don't test anywhere else, we only test at the CPs. Okay, so at 0, 0, D is -1. I'm just gonna simplify, skip the process for you. I'm just gonna let you go ahead and plug everything in. That means this is a setup point, right? Oh, never mind. I got this backwards. This is smaller than 0 and this is equal to 0, okay? Smaller than 0 equal to 0. So that means this is a setup point, right? Because the discriminant at the 0, 0 is smaller than 0 based on our second derivative test. And then we can test, we can evaluate the discriminant at 1, -1. This will give us 8. That means extrema exists, but we're not done yet. We need to continue to determine the sign of fxx. So fxx at -1, sorry, 1, -1. Right, so this will give us 3. I'm pretty sure that's 1, right? We just plug in 1 right here at the top. So we're going to get 3. So this will give us a local minimum. All right, let's try it one more time. We can test this at -1, 1. So that will give us 8 as well. And fxx at -1, 1 is going to be 3 again because we have x squared. So -1, 1 doesn't really matter. It's 3. And it's again the local minimum. So in total, we have 1 setup point and then 2 local minima. Okay? So in this case, the correct answer is alpha. So again, this is how you can find local extrema, solve the problem related to local extrema, right? Just find the partial derivative, find the partial derivatives, evaluate them at the critical, find the critical points, find the second partial derivatives, construct the determinant, and then we can use the SDT at this critical points, CPs, to tell whether these critical points are local minima, local maxima, setup points, or just inconclusive. Question number 9. By changing the order of integration, compute the following integral. Right, so this is obviously a double integral in general region problem, and particularly it is the changing of integration problem. Double integral in general regions, and then changing order of integration. Right, the key words is very simple, right? Changing the order of integration. Okay. So to solve this problem, by the way, before I go ahead and solve that, I'm going to mention that usually this type of problem are in rectangular coordinate, no coordinate system change. Required. Okay? So for any integral calculation problem, my approach is always to draw the region out. Okay? So first is draw the region. For changing of order integration problem, the only source of information we can use to draw the region are the integration bounds. Using the integration bounds. Okay, so let's take a look at the bounds. So we have dy dx. So these are the y bounds and these are the x bounds. So y1 equals to 0, y2 equals to square root of 1 minus x squared, x1 equals to 0, x2 equals to 1. So I think everybody at this point is comfortable with drawing such shape. So I'm just go ahead and do it, right? We have our coordinates of x, y, and then keep in mind, let's take a look at the x bounds first. X is from 0 to 1. That automatically eliminates the the regions on the left, right? The negative x-axis. We're not going to have anything here. And let's go ahead and take the y bounds, right? Y is from 0 to a square root number. So it's 0 to something with positive number, right? That also eliminates the bottom side of the coordinate system. So what we only have left is the first quadrant. And it's going to be just a quarter circle, right? And then y equals to 1 minus x squared. Okay? And then we're going to ask ourselves this question. Does the integral assumes horizontally simple region or vertically simple region? Okay, so the key difference between horizontally simple or vertically simple is that by looking at the integral, particularly by looking at the integral instead of the region, if the integrate was dy first, that means the integral assumes to be to have vertically simple region. So in this case, it is integrating with dy first, so the integral is assuming the region to be vertically simple, right? So since integrate with respect to dy first, that means it assumes vertically simple region. Okay, let me go ahead and then put these as in brown so that they are part of the example problem. Okay, and then we're going to change it to horizontally simple, right? As we should. Change the order of integration. Okay. So let's start with the inner bounds first, right? So the inner bounds is instead of dy dx, now we're going to have dx dy. So the inner bounds are going to be x1 is a function of y instead of a function of x, and x2 is going to be the same thing, right? x1 equals to f2 of y, and then y1 equals to a constant c1, y2, or just call it a and b. How about that? Right, and then dx dy. So that means we're going to formulate this circle, right? This circle with function with a function of y. So what that means, we're going to rewrite this this circle equation with respect to y. So I'm going to go ahead and skip many steps and just going to tell you this is x equals to 1 minus y squared. These two equations are equivalent. Right? I think with just some simple algebra, you should be able to arrive to this step really quickly. Right? So, and then and then let's take a look at the horizontal simple, right? So horizontally simple, we're integrating from the left to the right. So if we examine the left bound, right, this is our left bound. It's just a constant. It's just a number 9. And that number 9 on the x-axis is 0, right? So we have x1 equals to 0, and then x2 equals to 1 minus y squared, right? So we have x1 in the function of y equals to 0, and then x2 as a function of y is 1 minus y squared. So that means the inner side, right, this part of our integral will be 0 square root of 1 minus y squared dx, right? And then we're going to have the integrand itself. All right, so that's 3.1. Forgot to write down the solving step for you, right? I'm gonna call this process. I'm gonna formulate this process a little bit in terms of written English. Inner bound are functions of the outer integration variable, right? In this case, we have the outer integration variable is dx, right? So that means x, the outer integration is dy, so the x is a function of y. I hope this makes sense. And then this is our result. All right, and then 3.2, outer bounds are always going to be constant. Okay, so let's go ahead and go back to our plots here, our drawing here a little bit. Right, so we integrated from left to right first. Now we're going to integrate from the bottom to the right. So this is what horizontally simple is doing, right? So horizontally simple. Right, horizontally simple is always integrate left to right first, and then bottom to the top. Right? So now we're integrating from the bottom to the top. Right? So the bottom is a constant. What is this number? It's 0, right? So y1 is 0. This is number 9. And then y2 goes to 1. Okay? So now we can go ahead and formulate the final integral. So 0 to 1, and I'm just gonna go ahead and copy this thing down here, and then dy. And then finally, the final step we're going to solve, going to do to solve this integral problem is just integrate. All right, I'm just gonna go ahead and speed through this integration process for you, because I think at this point you are familiar with the integration process and should be pretty fast at computing these integrals. So 0, 1, and we're just going to integrate. So that's just going to be 1 minus y squared, and then dy. This will give us y minus y cubic over 3. From 0 to 1, that'll give us 2 over 3. And then this is the correct answer. Question number 10. Find the volume of the region bounded below by the surface and bounded above by the other surface, right? And then gave you a hint to use cylindrical coordinates, right? But what if I just go ahead and remove this hint from you? How can you still come to the conclusion that this is a triple integral in cylindrical coordinates? right? Hopefully I gave you some time to think about it, right? Well, the hint in this question prompt are these two terms. Well, whenever you see x squared and y squared taking on the same sign, right, you immediately think about x squared plus y squared equals to r squared, or c squared, a constant, right? That's a equation of a circle. But what if you might also ask, why don't I use spherical coordinates, right? Well, that's a good point, because if we try to remove the square root from here, this actually might be a circle. I'm not exactly sure, but I hope you see the x squared plus square. I hope you see the equation might take on the form of x squared plus y squared equals to z squared. Maybe not. But the reason why I don't use spherical coordinates is because here, z is only on the order of 1. Right? It's not a circle. It's neither a cone or a circle. So the keywords here is x squared plus y squared equals to c squared or r squared, right? And then we also have x squared plus y squared square root equals to r. That's another form of it, right? It's a potential or partial circular region. Partial circular region of integration. Okay, so now we know how to identify these type of problems. So let's go ahead and solve it, right? First of all, again, for any type of integral problem, I would draw the region. Well, the problem is it's interesting for this one, because this surface is actually really hard to draw. I mean, it's doable, but it's a little bit difficult. So I can write H. Hard region to visualize. Okay, but we can tell it's something that is circular, so cylindrical coordinate is still a valid choice. But let's go ahead and skip the drawing part and then start identifying the bound to see what we can do here. All right. Oh, sorry. Identify the integrand. Identify the thing that you're trying to integrate with, right? Does it give you an integrand? Well, they actually don't, but there is a keyword in the question prompt that tells you what the integrand is, right? Because we're computing a volume, whenever we're computing a volume using triple integral, the integrand is always 1. So since it's volume, f equals to 1. The integrand we're trying to integrate is 1. Okay? And then so we can go ahead and try to find the bounds of the integral. Right, so my approach is for cylindrical coordinates is oftentimes outside in. You can choose to do inside out, but personally I just find this one easier to follow, and then starting from the easy bounds and work my way up to the difficult ones. So what I mean by that is 3.1. So we're gonna start with theta bounds, right? I don't see any information inside the problem that's telling me that my angle of my revolution, right, or revolution around the z-axis is bounded. And so in this case, our theta bounds are just going to be 0 to 2 pi, right? And then and then I'm gonna work my way up to the to the r, right? So in order to find the bounds of R is I'm going to find the intersection between the upper surface and the lower surface. So the intersection between the upper and the lower what I mean by that, right? So we can rewrite the first z equation, right? So I'm gonna put this in brown, right? So z1 equals to 2 minus square root of 4 minus x squared minus y squared. And then z2 equals to 6 minus x squared minus y squared. All right, let's go ahead and convert them into the cylindrical coordinates. All right, so z1 equals to 2 minus 4 minus r squared. z2 equals to 6 minus r squared, right? And then we are going to let z1 equals to z2, okay? And then we're going to solve for r, okay? So z1 equals to z2, you give us 2 minus 4 r squared square root equals to 6 minus r squared. All right, let's go ahead and rearrange stuff a little bit. So we're gonna have actually r squared minus 4 equals to 4 minus r squared, and I'm gonna square both sides. R squared minus 4 squared equals to 4 minus r squared. Right, so we're going to have, let me rearrange this a little bit. So, and then we're going to have r4 minus 7 times r squared plus 12 equals to 0. Basically, you expand this squared term, and then you combine the common terms. So this will give us r squared minus 3 and then r squared minus 4 equals to 0. So hopefully you can tell that the r equals to root 3 or 2, right? We're not going to worry about the negative r values, because remember, our definition of r in this class is from 0 to positive infinity. We're going to ignore the negative r values. But note, if you actually plug in r equals to 3, z1 does not equal to z2 when r equals to root 3. So let's go ahead and try that, right? So by looking at this equation, right? So 2 minus 4 minus 3 equals to 6 minus square root of 3, right? So 6 minus 3. So 2 minus 1 does not equal to 6 minus 3, right? They just does not equal to each other. But what if we replace r with 2, right? So 4 minus 4, 6 minus 4, right? Now it's 2 equals to 2. All right, so this equation now is valid. So our valid r bound is r2 equals to, the outer bound is 2. So that means so r is belong to from 0 to 2. Okay? And then 3.3, let's go ahead and find the z-bounds, right? So z-bounds, I think the question has already given to you very explicitly, right? We want to integrate from this lower surface to the upper surface. So our z-bounds is just going to be z1 and then z2, but we're going to write it in the cylindrical coordinate format, which will be 2 minus 4 minus r squared, and then 6 minus r squared. Okay? And now final step, assemble the integral. Then integrate. Okay? Step 4 right here. Right? So now we're going to have volume equals to, right? So the integral will be dz dr d theta. And then for theta, where as we discussed before, is from 0 to 2 pi, and then from r is 0 to 2, and then for z is 2 minus 4 minus r squared, and then 6 minus r squared, and then the integrand is just 1. Let's go ahead and try to integrate this problem, right? So I'm gonna guide you way through it. So I'm gonna just focus on the innermost integral, right? So for this integral, we will have this will give us 6. Oh, sorry, never mind. I totally forgot, right? So this is, I made a really dumb mistake, right? So we need to have this conversion factor right here, from rectangular to cylindrical coordinates, right? So don't ever make a mistake like me, right? So it's r, I'm just gonna keep this one pink. So I'm gonna have r dz. So we're going to have r 6 minus r squared minus 2 plus 4 minus r squared equals to 6r minus r cubed plus 2r, or minus 2r, and then plus r times 4 minus r squared. Okay, so this is what we get from the innermost integral. So we're going to take this and then put it in the intermediate integration. So I'm going to copy this, paste it over here, the r. All right, so this is where it gets a little bit interesting, right? So we're going to make a u substitution right here. We're going to let u equals to 4 minus r squared. Du equals to 2 minus 2r dr. So dr is 1 minus 1 over 2r du. So we're going to substitute this dr right here, and we're going to substitute the u right here. So what we're going to get is, I'm going to separate these, right? So we're going to separate these integrals. Separate these integrals, and then we're going to leave the u substitution alone. Right? So we're going to move this into the u substitution. So we're going to have minus 1 over 2 u to the 1/2 power du, right? I think hopefully you remember your u substitution methods from Calc 1 or Calc 2, equals to, what do we have over here? This will be a minus 4 minus 0 for the left integral right here, for the left integral. And then we're going to have minus 1 over 2, and then 4 minus r squared. We're going to put the u substitution back in, and then 3 over 2, and then inverse of that is 2 over 3, right? So the 2 will cancel each other out, and then we're going to integrate from still 0 to 2, right? I would always like to put integrate with respect to my original bounds instead of trying to find the new u bounds. I just save some hassles for me. And this integral will give us 4 minus 1 over 3, 0 minus 4 minus 0, 3 over 2 equals to 4 plus 1 over 3 square root of 4, right? So 4 to the 1/2 is square root of 4, and then to the cubic, this will give us 4 plus, right, this will give us equal to 2. 2 to the cubic power is 8, and then 8 divided by 1 over 3 is 1 over 3, 1 over 3 times 8. This will be equal to 20 over 3. And finally, we have the theta integral, which will give us v, so the total volume equals to 0 to 2 pi, and then 20 over 3 d theta. This will give us 20 over 3 times 2 pi minus 0. This will give us 40 pi over 3. And that is the correct answer to question number 10. Question number 11. Compute the line integral as such, where C is the line segment from 0, 0 to 1, 2. Okay, so I think it's pretty obvious that this is a line integral problem, right? But there are two different types of line integral problem. One is in scalar field and one is in vector field. Which one is it? Well, the key is pretty simple to tell, right? Let's go ahead and write down line integral. Okay, right? The key is you identify the integrand that you're trying to integrate with respect to, right? So as we can see that this is a scalar function f of x and y, right? It's a scalar, not a vector. So this is a line integral in scalar field function, right? Line integral in scalar field function problem. Well, and then the keywords is just line integral as itself, right? And then scalar integrand f. Just f. It's fine. F is fine. Okay. So how we go about solving this problem, right? So first of all, I would always. Oh, by the way, for any type of line integral problem, the first thing is parameterization, right? You gotta parameterize, otherwise you will not be able to compute the line integral. So step 1, find expression of line R of t via parameterization. So this there are only a few methods of parameterization that this class has taught you, right? So one is just parameterizing for a curve, and sometimes they will give you the parameterization method. And in this case, where we are dealing with the most basic way of parameterization, which is parameterizing a line segment from 0, 0 to 1, 2. Okay. So so for this problem, R of t equals to t to t, right? So I think it's pretty easy to go ahead and formulate that equation of a line, right? And equation of the line is parameterized with respect to t. So x of t y of t, right? And then we also need to find the range of t, right? For me, I want to make make my life easy when I integrate, right? So the reason why I set it up in this case is instead of 1/2 t and then t, is so that my bounds of t is just 0 and 1, right? Instead of 0 to 2, right? I want to make my life as easy as possible, right? For let's say for an example, when you try to and we just want to make our life easier. Second step is to find r of t prime, r prime of t, then the magnitude of r prime of t. Okay, so r prime of t equals to 1 and 2, so that the magnitude of r prime of t is going to be √5. Okay, but parameterization we're not quite done yet, because if the line segment is parameterized, the function itself also needs to be parameterized. So, and that's what we're going to do next. Parameterize function of f, y, z, right? We don't have a z in this case, and get f of x t, y t, z t. Okay, so in this case, f equals to, now what do we have? F is 4x cubed plus 3y cubed, right? So then f of t, x of t, y of t, z of t, right, which is just f of t, right? It will equal to, right, whenever we see an x, right, whenever we see an x in the function f, we plug in the parameterized coordinate of the r of t, right? So what we're going to end up with is 4t cubed plus 2t, right? That's y to the cubic. And this will give us 12t cubic. Okay? And then step 4, now we have all of the information that we need to assemble the line integral in scalar field problem, which is going to be a to b f x of t, y of t, z of t, and then multiplied by r prime of t in magnitude dt. So this will give us 0 to 1, 12t cubic √5 dt, right? I'll make my life easier. We're just gonna have 12 √5 over 4 times t to the 4th, 0 to 1, right? We're just gonna have 3 √5, and that is the correct answer, which is alpha. Question number 2. Compute the line integral where f is such and then the curve c is parameterized by r of t, and then t is from 1 to 2. Okay? Well, this again, it's a line integral problem, right? Line integral. But again, which type is it? Is it a scalar or is it a vector? Right? I think now you have understood my technique of identification, right? We just go ahead and going to take a look at the integrand itself, right? In this case, right, we have a line integral as a giveaway for line integral problems, and now instead of a scalar, now we have a vector as our integrand. So this tells us this is a vector field, right? Line integral in vector field problem. So the giveaway is, first of all, CDS. Let me go ahead and make that up right here as well, right? CDS. This is the standard notation for line integral, right? And then we have vector integrand, usually denoted by capital F. And then, or sometimes they will give you some sort of live real world example. In common cases, work done, right? So people who took physics, work is just force times distance. So to solve these type of problems, right, again, we're going to parameterize the curve, right? Parameterize the curve, right? In this case is done, right? And the range of t, right, a, b, this is also done for us, right? So I'm just gonna go ahead and copy this down. T squared t cubic minus 3t t1 minus t2, right? Or I'm just gonna go ahead and write them as t, right? T belongs to 1 and 2, right? This is your x of t, this is your y of t, and this is your z of t. All right. So second thing we're going to do, which is a little bit different from the scalar field line integral problem, we're going to find r of t. That's it. All right. So that's just r dx dt dy dt d. You know what it is. We don't need to go through this, right? So in this case, r of t, r prime of t equals to 2t 1 3t minus 2. Okay, and then the third thing we're going to do is to parameterize the vector field f of x, y, z, and get the same thing, f of xt, y of t, z of t. Okay. So f x y z equals to what do we have here? Y z x z x y. Okay. And then if we do our parameterization, if you follow our parameterization, or f of t, x t, y t, z of t, f of z, y of t, z of t gonna be equal to t cubed minus 2t t squared t cubed minus 2t t squared minus t, right? So this is just y, this is z, this is x, this is z, this is x, this is y, right? So this is just our original vector field parameterized. So your final step is just going to be plug in the definition, right? So the line-integral problem in a vector field is just going to be f dot dr, which equals to going to be cf dr dt, and then dt equals to be you're gonna have right, so we have f, we have f right here parameterized, we have dr dt right here parameterized, and then we know what the bound is. We also have that, so we're just gonna go ahead and plug everything in and compute the line integral. right? Okay, so for people who have been very careful about this problem, I want you to take a close look of this vector field, okay? Especially for people who hasn't noticed what's the secret about this vector field is, well, let's take a look at the x component, right? We have yz. Which variable is missing? X, right? Well, let's take a look at y variable, right? This is y variable is missing, right? And then finally, the z component, z is missing. Do you see a pattern here? Right? What could have gotten my z these variables away, right? Could I have eliminated these variables by differentiating of the same function? That's a possibility, right? And then what is that function called if that exists, right? I think you should recognize that this function is called a potential function. A potential function might exist for this problem. And then if that exists, we can take advantage of the property of line integrals, which using the fundamental theorem of line integral. Okay? So this is actually not a line integral in vector field problem. Well, it kind of is, right? But indeed, it's actually, let me just go ahead and copy this for you. Right, so this is, copy this for you. This is a line, it's actually a fundamental theorem of line integrals. Right, so the key word is it has to be a line integral in scalar field, in vector field problem. Okay, it has to be. Okay, and then the vector field has to be conservative, right? If we do a quick check, you will find it conservative. Okay. And then another thing, I don't know if you noticed from our previous approach that this line integral in vector field suddenly got really difficult to compute, right? If you take this dot product between the two, that's already difficult enough, and you have to sum up everything and then integrate again, right? It's really a huge hassle. So usually, this line integral is hard to compute. Okay. So how are we gonna solve this type of problem? Okay. So the first step is you have to identify whether f is conservative. Right? So it's wise to check every vector field, every vector field in your exam is whether it's conservative or not. But it's really time consuming to do so. I hope you agree with me, right? You can check, in a two variable case, right? So fy equals fx, right? Right. Sorry, the fxy. Sorry, never mind. Assuming this f is the derivative of psi x, psi y, phi x, phi z. So what we're going to have is actually, I'm going to use psi. No, it's too ugly. Let's just go ahead and use phi. Okay. So f equals to phi x, phi y, phi z. Okay. Then for it to be conservative, right? F phi x y, right? Taking the derivative with respect to y has to be equal to phi y, taking the derivative with respect to x. Right, we do this again. Phi x z equals to phi z x, phi phi y z equals to phi z y. Right? It's just really a big hassle. Right? I mean, it's yes, this is a formal way to check it, but it's a really big hassle. So what I'm going to show you, sort of a shortcut to identify this is, I'm just gonna go ahead and copy my notes down for you, because I think this is really helpful for you to identify, right? Where is it? Right here. Right. So these are the sort of I call them the shortcuts that's useful to quickly identify which vector field is conservative, right? So let's go over them, right? First of all, you have similar and repeating terms in f, right? So let's look at this example, right? yz, xz, xy again, right? So it's again two terms are showing up together, and then this one x is missing, y component is y missing, z component is z missing, and you also have this common and repeating term e of x, y, z available in your vector field, right? So that's one way that you can tell that this is a conservative vector field. And the second way is the variable in its vector component has one less order, right? So let's, for example, right, the x component, right, x is missing, right, has one less order, right? Y again missing, one less order. Z missing, one less order. And then the one vector component resembles the derivative of other components, right? So for example here, right, sine and cosine are quote unquote the derivative of each other, right? So in this case, that if you see some sort of trigonometric ones that sine and cosine are showing up together, there is a chance that a vector compensable function exists. Okay, so I've rambled a lot over here. I hope you understand these shortcuts. So I'm gonna call this step 1, and then step 2, we're going to find the potential function, right? So step 2, find potential function phi x, y, z. Right, so this is another shortcut that I'm going to show you, right? So I think I'm pretty sure the professor have told you, right, we should start with the x component, integrate that component, and then put a constant, and then differentiate again with respect to y, and then match the components, all that jazz, like, you know, basically a combination of integration and differentiation, and again and again and again, until you arrive at the potential function, right? That's fine. If you're not comfortable with that, keep doing it. But I just think it's really tedious way of doing it, and then there's a much shorter way of doing that, much faster way of doing that. Okay, so let's so what I'm going to do is, right, so 2.1, so I'm going to show you how to find the potential functions really quickly. Right, so I'm going to say integrate each component of f with respect to its component variable. What do I mean by that? Right, so let's take a look at this case. Right, we have f, right, f equals to psi x, psi y psi z, I think it's psi or whatever. I'm just gonna keep putting psi, and equals to yz xz xy, right? So what I mean by that is just partial psi x dx equals to yz dx, right? This will give us xyz, and then we're gonna do the same. We're gonna play the same game. I'm gonna duplicate that again. Okay, so we have psi y dy, and then psi z dz. Right, so this will be our y component of the f vector field. This will be xz dy, and then xy dz. Right, the end result will be xyz, nonetheless. Right, and then the second step is to what I call find the potential function phi x, y, z by finding the union of all integral products, and then plus an arbitrary constant. Okay, so what do I mean by that, right? So psi of x, y, z just gonna equal to this, the union of this. Dx, I'm gonna over here, and then not plus, it's a union of y and z, same thing. Okay, so in practice, what does it mean for this particular problem? Right, so we're going to have equal to union of x, y, z, union of x, y, z, x, and then union of x, y, z. Right, this is just going to equal to x, y, z. Right, the union of this is just we're counting, we're adding all of the terms, but not double counting the duplicates. Okay, and then we plus c. Okay, oh, forgot about the plus c. Right, so that's all there is to it. Right, that's all there is to it. And then there you go. This is our potential function. Okay, and then step 3, we're going to identify the time interval which it belongs to, a and b. Right, so in this case, t belongs to 1 and 2. And then step 4, we're going to do find r at a, and which equals to x a y a. You know what? I'm gonna disregard this, and then rb. Right, I think just you know how to plug stuff in, so I'm just gonna go and skip that. R of 1 equals to so R equals to what is R in this case? R is T. You know what? I'm just gonna copy it from where? From here. Okay. R of T equals to this. Right. So R of 1 is just gonna equals to 1, 1, -2. R2 just going to R2 just going to equals to 4, 2, 2. Okay. So finally, we're going to substitute one more step before the final step. I sub R of A and R of B into psi of x, y, z, get psi of RA and psi of RB. Anyway, 6, the final step is going to take advantage of the line integral, fundamental theorem of line integral, which is defined as such equals to R of A minus R of B minus R of A. Okay, so for us, this equals to oh, by the way, I forgot to mention this step right here. So psi of R of A equals to we have x, y, z as our psi, so that's just gonna mean we're going to have 4, 1, 1, -2, right? So x, y, z plus c minus 4, 2, 2 plus c. X, y, z. Now you can see that the c cancels out. So, sorry, never mind. Never mind. This is psi RB. Making a lot of mistake here, but I hope you are following my process. And then we're just gonna equals to, what is this equal to? Anyway, this is gonna equal to what is this? 16, I believe, right? So we have this equals to 16 plus c, and then we have this one as -2 plus c, right? So 16 plus c minus 2 r plus c, and then we're going to have 18. So that is a shortcut to line integrals in vector field problem if and only if the vector field is conservative. Okay? Question number 13. Compute the following line integral for f where c is the curve bounding the rectangle with the 4 corners oriented counterclockwise. So what type of question is this? This is a Green's theorem problem. Particularly, it's a Green's theorem in circulational form. So how do I know that? Okay, let's go and write it down. Theorem, circulation. So how do I know that this is a Green's theorem problem, right? Okay, so Green's theorem problem for the circulation is particularly defined as this integral of CF dot dr. Okay, it looks like a regular line integral in vector field definition, but the Green's theorem circulation flow form on the line integral side takes on this form. Okay, so I'm just gonna write down over here, right? If the question asks you to compute this, right? So this is your the n is your normal vector. That will normal vector of the curve. So this will give you the flux form. Okay, so f dot dr corresponds to circulation form. But there's another important detail that we need to pay attention to in order to determine whether it's a regular line integral in vector field problem or it's this Green theorem problem. And that key difference is that the curve is bounded or closed curve. It's a closed curve, not an open curve. It's an open curve, you can never use Green's theorem, right? Green's theorem is a translation between a line integral and an area integral, right? So area integral, the curve must enclose itself to form that area. Okay. So I'm gonna say this is a closed or bounded curve. Okay. So, and another oh, by the way, I'll get to that later. So first of all, to solve this kind of problem, I would always encourage you to draw the region. Okay, so in this case, this is a pretty easy region to draw, so I'm gonna go ahead and go through this really quickly. Right, so that's 1, 2, 2, 1. Okay, and then second, determine whether it's easier. We're going to determine whether it's easier to compute the line integral or the area integral. Line or area integral. Okay, so how do we make that judgment call, right? Well, let's take a look. If I want to compute the line integral, how many line integral do I need to compute? We have 1, 2, 3, 4. 4 line integrals to compute. That means 4 different kinds of parameterization and 4 different integrals to compute. Well, that's not really easy to do, right? So, but what about an area integral? Is the area easy, right? It's a rectangle. It's a very easy type of double integral, right? And we only have one double integral to compute, right? So in this case, area integral is much easier. So the reason why we are making this judgment call is because Green's theorem applies both ways. Sometimes it is much easier to compute the line integral compared to the area integral, right? Let's say the area looks really ugly, but the line somehow is very clearly defined, or they already gave you the parameterization form, right? That's when you should compute the line integral. But in this case, area integral is much, much easier. So let's proceed. 3, let's go ahead and identify. I'm going to go ahead and put down the definition so that we can follow the process along the way. So I'm going to have F CFDR equals to CF f dx plus g dy equals to region of gx minus fy dA. So in order to use this theorem, we're going to identify f and g first. This is not a very easy step to do for some, and this is not exactly. It's just an easy step to do, but we need to do that, and then so that we don't get confused later on when we try to take derivatives. Okay, so f equals to y squared, g equals to xy, and then we're going to find g fy and then gx, right? So that's the corresponding term that we need to find in the area integral. So then fx, so fy equals to 2y, gx equals to y. All right, step 4, what we're going to do is find gx minus fy. Okay, so gx minus fy equals to y minus 2y gives you negative y. All right, finally, we're going to use this Green's theorem in circulational form. All right, so we have all the things that we need to construct our integral. So we don't compute this part. This is the line integral part. This is the area integral part. Right, we're only going to compute this integral. So this will give us. All right, so we're going to be. It's going to be the integrand is going to be gx minus fy. That's just negative y. Right, and then we're going to compute this in the rectangular coordinates. So let's just go ahead and do with easy way dx dy, and then x bounds will be 0 to 2, y bounds will be 0 to 1. Right, this will be a very, very easy integral to compute. So I'm going to go ahead and plug it away. So that's just going to be 0 to 1, negative 2y dy. And this will give us negative y squared, 0 to 1 equals to negative 1. Okay, and this is the answer to question number 13. Okay. Question number 14. Compute the following integral where the curve C is a boundary of a half disk of x squared plus y squared smaller than equal to the line, and then x squared is in 0. Okay, so this is actually again the Green's theorem problem, and it's again a circulational form problem. Right, so what we have said before still stands true, right? So first of all, this is a closed curve. This is a closed curve, right? Closed curve or bounded curve. But this time we don't have the f.dr available anymore. But a huge giveaway, and this is what I want you to remember, is that if the dx term, right, if the dx term is positive, right, I'm gonna write that down, positive dx term in your in this kind of weird looking form of line integral, positive dx term, this means circulational form. Okay. Okay. So so in the opposite, right, if it's negative, the x term flux form. And this is the easiest way to differentiate between whether it's asking for a circulational form green theorem problem or flux form green theorem problem. Okay? So if it's and then so this in the area this is the line integral case, right? So it's a positive dx term. But what about in the area integral case? So if it's area integral, we are going to have the gx minus fy, okay? So term in the area integral. So circulational form. And then if it's oh yeah, and that's pretty much it. So this is another additional hint that's not available in this question, okay? So how do we gonna solve it, right? Again, first of all, draw the region. Right, so in this case, this is a half circle, and then with radius of 3, and only on the right hand plane. So like this, half circle. I drew it very poorly, but doesn't really matter. And then we're going to have 3, negative 3, 3, right? Draw the region out. And then we're again going to determine, so I'm just going to go ahead and copy and paste right here. Determine whether it's easier to compute the area integral or the line integral. Okay? So we're going to make this call again. So let's go ahead and analyze this graph. Analyze this graph. To complete this bounded curve, we're going to have 2 separate lines or curves to complete the bounded curve, right? That means 2 parameterizations, 2 line integrals. Just not fun, right? But look at the area that's covering, right? It's a half circle, right? Half circle, what coordinate can we use? We can use polar coordinates, right? And then we can create a double integral in polar coordinates to make our life a little bit easier. So again, in this case, area integral is again much easier to do. So we're going to just go ahead and repeat the same thing. So we're going to go ahead and identify f and then g, and then identify fy and f, and then find fy fx, fy gx. So in this case, f will always follow in the circulational form. F will always follow the dx term, and then g will always follow the dy term. Okay, so f equals to y squared, g equals to x, and then this will give us fy equals to 2y, gx equals to 1. Okay, and then step number 4, we're going to find gx minus gfy. So gx minus fy equals to 1 minus 2y. And then finally, we're going to compute this area integral again. Same thing as question number 13. So in this case, we will use polar integration. Okay? So I'm going to skip all of the conversion for you because at this point, I think it's pretty easy for you to know how to compute a double integral in polar regions. So I'm just going to go ahead and write it down for you. So negative pi over 2 to pi over 2, right? And our radius will be 0 to 3. That's the radius of the half circle. And then 1 minus 2y, and y is r sine theta. And then we're going to include the conversion factor r d theta. And then we'll go ahead and compute this integral for you really quickly. 0, negative pi over 2, pi over 2. And I'm going to have 9 over 2 minus 18 sine theta d theta equals to 9 over 2 pi over 2 minus negative pi over 2 minus 18 cosine pi over 2 minus cosine negative pi over 2. Right? Cosine of negative number is the same thing, so this thing gets canceled out immediately, and then we will have 9 pi over 2. Okay, and then one last thing to mention, right? Note that we are going to use a clockwise orientation, right? This, for normal parameterization of a circle, we always follow the counterclockwise orientation. So this is not a normal orientation. Right? So because of that, and then because of we use the normal orientation, right? We assume this integral, the parameterization follows from negative pi over 2 to pi over 2. This is a counterclockwise orientation, right? It's the opposite of what the question wants. So step number 6, if used opposite orientation, or if opposite orientation required, right, stick with normal orientation when calculating integral then flip the sign of integral value at the end. Okay, so in this case, the correct answer is actually negative 9 over 2 pi equals to negative 9 2 pi. And the correct answer is D. Question number 15. Given a two-dimensional vector field F, compute the value of a scalar curl at 0.21. Okay, so this is I think by the name of the property that we're going to compute, it's pretty obvious that this is going to be a divergence and curl problem, right? And particularly, this is going to be a two-dimensional curl, right? So I'm just going to write it down, right? So this is going to be divergence and the curl problem. Okay, so the key word here is, curl, right? Or divergence. So, and then so the solving step here is what I call it just, just do it. Right, so this is just a very, very fundamental and definitional problem, right? So, but what's interesting about this question is, it's asking for a scalar curl for a two-dimensional vector field. Okay, so So I'm gonna show you something that's a little bit different, and then show you a little bit of derivation of how it came to be, right? So for 2D vector field, F equals to G, F and G. Okay, scalar curl of F equals to the determinant, or I think that's what it's called, of the del operator in 2D. That's partial x, partial y, cross product with F and G. That's cross product, never mind. And in the K direction, so that's the Z direction. Okay, so this, if you do the cross product, right? So do the cross product right here, right there. I'm gonna label this in blue. So you always go down first stroke. You go down first stroke, and then you go down second stroke. So you're gonna have Gx, the first thing, and you're gonna get Fy at the second thing, right? So that's your scalar curl. Okay. And then for scalar divergence, just to, for the sake of completeness, that's just your del operator, partial x, partial y, in the 2D world, dotted with your F and G. Okay, so this just simply gives you Fx plus Gy. That's it. And then, so in this case, we're going to compute the Fy, right? We're going to compute Fy equals to, I'm just going to compute this really quickly. So let's keep in mind these two vector fields. I'm going to go ahead and copy them. Fxy equals to x squared plus y, x squared plus y squared, x minus x squared plus y squared, so let's go ahead and put this down. So Fy just gonna be equals to, I'm just gonna compute these partial derivatives really quickly. X squared plus y squared times 1 minus y 2y over x squared plus y squared 2 F y 2 1. About 5 minus 2 over 25 equals to 3 over 25. Okay. Gx equals to 1 minus x squared plus y squared times 1 minus x times 2x x squared plus y squared squared. Okay, and then Gx at 2 1 equals to 1 minus 5 times 5 minus 8 over 25. That will give you 28 over 25. So Gx minus Fy equals to 1. And that is the correct answer to question number 15. Question number 16. Find the surface area of the parametric surface, right? So this is and I think everybody agrees that this is a surface integral problem, right? So surface integral problem, but again, like the line integral problem, there are two different types of surface integrals, right? is this in scalar field or is it in vector field? Right? So the key here that is that this is a surface integral in scalar field is because we are trying to compute the surface area, right? Area is a scalar, so this is a scalar field surface integral. So scalar field. But we haven't quite finished yet because we not only need to identify whether this is a scalar field or vector field problem, we also need to identify whether this is a explicit surface or implicit surface, right? By looking at these components, vector components, right, we see that x is not just u, right? Or y is not simply just v, or vice versa, right? What that tells me is that x is a combination or combination of u and v, and same as for y as well, right? If it's explicitly parameterized, we're going to have u, v, and an f of u and a v. So this is clearly not the case. So this is an implicit surface, okay? So implicit surface, right? So we're going to have, so keywords here is surface area, surface integral, and then area, right? So this is scalar, and then R is and then also R is takes on the form of x u v, y u v, z u v. All right, so this tells you implicit. Okay, how are we going to solve this problem? Well, we're going to start with a few things. So we're going to parameterize the surface R, and then the integrand f, right? We not only need to parameterize the surface, and also need to parameterize the integrand itself as well. But this is done for me for the problem. And you also need to convert the coordinates and then change and find the bounds of u and v. And this is also done for us by the problem. So we can move on to step number 3, which is going to be finding r u equals to partial r partial u, and then rv equals to partial r and a partial v. Okay, so in this case, ru is just going to be 2, 3, 0, right? You can compute this partial derivative really quickly, and then rv equals to 3, 1, 0, right? You just take the partial derivative of this r of u and v. Okay, step number 4, we're going to find the cross product of partial r partial u, and then partial r partial v, cross product, then the magnitude of it. Okay, so we're going to find that. So r, I'm just going to simplify my writing here a little bit. So r of u times r of cross of r of v, we're going to get is 0, 0, negative 7, right? Just by taking the cross product of this vector and that vector, and then the magnitude of this whole thing is going to be simply 7. Okay, and then finally, we're going to just go ahead and assemble the surface integral, which is going to be
surface integral, your integrand f x y z ds. This is a big S that indicates the surface, equals to S of f x u v y u v z u v. This is just definition. Don't be scared by the lengthiness of it. It's just simply definition, and we're going to have partial r, partial u, x, partial r, partial v, d, a. At the end of the day, it's just a double integral. Nothing to fear. Oh, this is R notation, not S notation. And then we're going to keep in mind to ourselves that note that this definition, R1 times this whole thing, equals to surface area, right? Since f equals to 1. So this makes our problem a lot simpler. And then I'm going to keep in mind our bound is just going to be 0, 1, 0, 2, 7 d u dv. Right, we're going to copy this and then paste it. Right, so the 7 is what we get over here, right? And then dA is just du dv, and then our bounds just from 0 to 2, and our answer will be 14. And that's it. The correct answer is 14 for question number 16. Question number 17. Let S be part of the plane y plus z equals to 10 that lies inside a cylinder. Compute the surface integral for f with S oriented by the upward normal. Okay, so I think everybody understands that this is a surface integral, right? So because we have a definition right here, so surface integral, right? But we're not done yet, right? We have a few things to identify before we can start our solving step first. Well, for question number 1 is it explicit surface or implicit surface, right? By inspecting this equation, a plane, right, S be the part of the plane, one would quick to draw the conclusion that this is an implicit surface. But remember, the surface integral for implicit surface is much more lengthy and tedious to compute than the one for explicit surface. So if there's any chance that we can convert from implicit to explicit easily, we will take the opportunity, right? And this is the opportunity. So we can convert this into z equals to 10 minus y becomes explicit, right? Well, so we can take advantage of explicit surface integral definition, right? But also, is this a surface integral in scalar field or vector field question, right? Again, we take a look at our integrand here, right? F is a vector field, so this is a surface integral in the surface integral in vector field for explicit surfaces. Okay, so the keywords is, first of all, you have F as your vector field, right? And then you also have z equals to function of x, f of x and y, right? So this is your explicit surface definition. So these are the two things that we need to pay attention to. And now, of course, you also have the surface of S, and then ds as your surface integral definition. Okay, so first thing to do is we're going to parameterize, right? Again, for line integrals and surface integrals, the first thing that you need to do is parameterize, right? Parameterize. I cannot stress this enough. You gotta parameterize before you do line integrals and then surface integrals. So first of all, parameterize. parameterize the surface R as well as the integrand F, right? So y plus z equals to 10. This becomes z equals to 10 minus y, right? So we can, this is a fairly straightforward way of parameterizing, right? There's nothing fancy that's going on. We can just let r of, u and v, or x and y. So I'm gonna make my life a little bit easier. Just call it x and y in here, right? So x and y equals to, well, is x present in this equation? No, right? X is not present in this equation. So we're gonna parameterize x with just 0. And then what about y? We can just let y equals to y, and then for the z equation, we're just going to let z equals to this equation, right? So z equals to 10 minus y. Okay? And the second thing we're going to do is, sorry, my bad, was one more thing that we forgot to do. So f, right, now we have r of x and y. Now we can parameterize this vector field f, right? F equals to, we've already done it, right? The question has pretty much already done it for us because we are parameterizing this vector field explicitly. There's no need to convert any variables, so that's already done for us. So x, 1 minus y, plus e to the z, and then y, e minus z, minus e to the z, right? Now we have our surface and our vector field written in our parameterization variable x and y and z. Okay, actually, never mind. I take that back. That's not done for us. We still gotta replace all of the z with respect to our parameterization variable x and y, and that's easy to do, right? Z we just replace with 10 minus y, and then 10 minus y, and that's all the parameterization that you need to do, right? Not too difficult. Okay, and then second thing that we need to do is to find RU, right, the partial derivatives, RV, then N equals to RU times cross product with RV, right? And this for implicit surfaces, it's a kind of tedious way to do it because I have to do the partial derivatives and then you take the cross product. But for explicit surface, life is a little bit easier. What I mean by that is this equals to negative zx, z with respect to x, negative z with respect to y, and then 1. It's always this way. For explicit surface. So by inspecting z equals to 10 minus y, we can conclude that zx equals to 0, zy equals to negative 1. Therefore, the normal vector equals to 10, 0, 1, 1. Okay? And the third thing that we need to do is to compute the dot product between f and n. Right, so this will give us x. I'm just gonna take the whole thing down. Right, we have the parameterized version of f right here, and we also have parameterization version of the n right here. Right, we dot product them. This will give us 0 plus 1 minus y, the whole thing right here. All right, let me just make it a little bit nice, look nicer and tidier. Right, make it look nicer and tidier. Okay. Okay, and then plus another term in the z component times 1. We just move it down right here. This will greatly simplify for us, right? So the positive and negative e term cancels out. The y term, positive negative term cancels out, equals to 1. Right? So finally, we can go ahead and compute our surface integrals. And then the definition is as follows. The integral of s, f times n ds equals to positive or negative r f x y z is function of x and y, and then dotted with negative zx, negative zy, 1 dA. Okay, so for this example, right, we already have computed so let's go ahead and just start with constructing this integral very slowly, right? So we have r, and then our integrand over all this whole thing equals to 1, as we just computed, dA, right? And let's go back to our problem statement, right? This plane is bounded by the cylinder, right? It's a cylinder. What does that tell you? Which 2D coordinate that we should use, right? Because at the end of the day, surface integral is a surface integral are at the end of the day a double integral, right? So which 2D coordinate we should use, right? It's polar coordinate we should be using because it's a cylinder, right? It's something circular that we should always thinking about polar coordinates. So we're going to use polar coordinates right here, right? So and then the integration again, very simple, right? It's a r 1 times r dr d theta, because it's a cylinder of radius 1, so 0 to 1, and then there's no bound for the angle, so just 0 to 2 pi, and this will just give us 0 to 2 pi r squared over 2 the from 0 to 1 the theta. This will, and then we will get 0 to 2 pi 1 over 2 the theta equals to pi. Okay. One more thing to note is this question is asking for upward normal, right? So upward normal, this is an normal orientation. When we try to parameterize this, surface, upward normal is usually the normal orientation of the surface. Okay, so if it's asking for the downward normal, we are just going to flip the sign of the integral result after we follow through the normal orientation method, just so that our brain doesn't get confused of a different way of parameterization. Okay? Question number 18. Consider the following vector field where r is x, y, z, and then the magnitude of r is magnitude of r. Which one of the following is true? Okay? This is a classic radial vector field problem. Okay, radial vector field problem. And then the keywords is simply these definition of the radial vector fields. So r of r cubic, right? These are the ones. So I'm just gonna go ahead and copy them down right here. F equals to magnitude of r cubic, and then r equals to x, y, z, and then the magnitude of r is x squared plus y squared plus z squared square root. Okay. So to solve this type of problem, there really isn't any sort of steps that you need to take, but instead it's a number of definitions or properties of the vector field that you need to memorize to solve these problems. So first of all, F is conservative. So you remember from your conservative vector field chapter, right? That means if you apply the fundamental theorem of line integrals, which is applicable, you'll realize that the line integral in vector field f star dr is path independent. Okay, path independent. So that's property number one. Property number two. Oh, before I do that, let me just go ahead and bring some example to you of what these vector field problems are. So what are the real life examples of these vector fields? So example. So let's say a light bulb, right? Sun, right? These are like example of using light. We can also use universal gravity. Right, so these are very good examples of inverse of the radial vector field in real life, and we're gonna help us use these examples to illustrate these properties. And number two is curl of f equals to 0, and then divergence of f is also 0. Okay, let me explain. So let's say we have a light bulb, right? We have a light bulb, and then this is the core of it. This is where it's shining, right? This is where it's shining through the light, and then this is the sort of the light bulb, glass that's covering it, and then I think everyone understand that these vector field will flow radially out, right? Right, flow radially out. So let's draw that more obviously. Right, but you get the idea. Okay, so I think it's easy to see that there's no rotation in this vector field. So the curl of f is 0. But why the divergence is 0? Okay, let me explain. So let's say this is our glass, we call them S1, right? The surface of this glass surrounding this light bulb is S1. Well, what if I replace this sphere, this glass with a bigger glass, right? We move this and we have a bigger glass, right? So we call this S2, right? And I want you to compute the surface integral, and I'll bring up definition number 3 as well, right? The surface integral S of and F dotted with N ds, right? I think everybody would agree with me that since there's light flowing through the light bulb, right, the glass, the surface integral in vector field is going to be greater than 0 for any closed surface. Okay. So, but I want you to take a. But do you think what do you think the value of this surface integral that we take right here compared to this one? Right. The value of these two surface integrals, S1 and S2, will equal to each other. Okay, hold on a second. Why is this the case? Well, let's think about it, right? If we standing away from the light source, right? If you're standing away from the light source, the lights will be dimmer, right? So that means there's less light flowing through each unit area, right? Even though the amount of light flowing through it doesn't change, but each surface, each unit area gets less light, gets less flux from the light bulb, right? So the area increased, but the flux per area decreased. So they end up equaling to each other. So that means there's no new photons is generated from here to there, right? So that there's no tendency of the vector field to increase, right? So that's why the divergence here is 0, because as we go further and further, the amount of flux doesn't change. Okay? So let me continue with my definition. Okay? Number 4 is that divergence theorem does not apply or is not valid at origin. Okay, so this is a really big deal. Because, why is that? Because at origin, F equals to dne. It's 0 over 0, dne. Okay, so that means so that just simply means that even though we have so let me go ahead and put down the divergence theorem right here. Fn ds does not equal to the divergence of f dv. Okay, so we cannot use we cannot translate from the surface integral from the divergence integral, because many people would think that, oh, let's take a look, right? We have that vector field flowing over here, and we certainly have another vector field. We have a vector flowing out from this direction. We certainly would have another vector field equal in magnitude but opposite in direction to this vector. So they would think that the divergence of this equals 0, right? I mean, hold on a second, right? As we have proved, right, the divergence of f is 0, right? So on the left hand side, this will equal to 0, right? But because divergence of f is 0, and on this side, this is non-zero, right? This is greater than 0, right? So I hope my illustration shows you that why divergence theorem is not valid at origin. Okay, so based on these 4 properties that we have, we can go ahead and take a look at the answer choices, right? So first of all, line integral f dot dr is path independent, as we discussed, right? That's your first definition. So this is the correct part of the correct answer. And then f and then this surface integral equals to 0 for any closed surface that encloses the origin, right? As we discussed, right? There are lights shining through these light bulb glasses, right? There's no way that the surface integral is equal to 0 for any enclosed surface. So this is not true. And then divergence of f equals to 0. That's just the definition as we have discussed. So the correct answer is C, right? As once you understand and memorize these definitions, it becomes a radial vector field problem becomes very easy to solve. Question number 19. let the vector field be as such, compute the surface integral, where S is part of the graph of z equals to function of x and y below the xy plane with downward pointing normal. Okay, so I think for many people, they would just quickly to draw the conclusion that this is a surface integral in vector field problem. Okay, but this is not the case. In fact, this is actually a Stokes theorem problem. And especially because this is a theorem problem, they can ask you a question both ways. And in this case is given a surface integral, but compute must solve via line integral. Right? They didn't even tell you that this is a Stokes theorem problem, but in fact, this question is much easier to solve, and this is the correct approach when you want an exam to solve this type of problem. Well, how do I know that this is a Stokes theorem problem? Right? So the key word, first of all, it is that they gave you the surface integral side of the Stokes theorem. Right? So the Stokes theorem, surface side of Stokes theorem, right? So which is, W integral of S, gradient of del cross F, and then dot N ds. Okay. And then just by another sort of informal way of telling that this is a Stokes theorem problem is because look at these integral. This is a really hard integral to compute for, right? So this is a really hard vector field compute for, and then this this S is this graph this function is also a very difficult function to compute. Okay, so first of all, right, to solve this type of problem, we're going to determine whether the surface or the boundary is easier to integrate. Okay, so in this case, right, let's examine this surface, right? So it's this surface below the xy plane with a downward pointing normal. So let's go ahead and draw this isometric view out, right? So this, I don't really know what this means. So, but at the end of the day, I think everyone can agree that it's sort of a number. It gets bigger, it gets smaller. Sometimes it can be bigger, it can be smaller. But I'm just going to focus on this part, right? X squared so let's say z equals to some sort of number times x squared plus y squared minus 36, right? What does this look like to you? Well, this looks like something of a paraboloid, right, with a z-intercept of negative 36. So when we add z equals to 0, x squared plus y squared equals to 36, which is 6 squared. So this should be a circle with a radius of 6, and then with the parabola pointing downward, right? So reaching this intersection right here, right, negative 36. So let's go ahead and take a look at the surfaces, right? So again, we have two surfaces, right? One is sort of the side of the sort of the wine glass, the paraboloid, and also we have the face of the circle, right? The sort of the top of the wine glass. So we have two surfaces to compute, but if we look at the boundary line, right, there's only one boundary line, which is this thing in pink. I'm just gonna highlight it for you, right? There's only one boundary line that we need to compute, right? Two surface integrals, one line integral, right? You tell me which one is easier, right? Of course, line integral is much easier. So now we have determined that we're going to use the line integral, solve it via the line integral problem, right? Which is the standard procedure of these theorem problems, right? They gave you this definition, but they don't really want you to compute using this definition that they gave you. Instead, they want you to use the other side of the theorem. Okay, the second step will be find the curve C, and then parameterize it. You gotta parameterize, right? You gotta parameterize for every line integral and surface integral problem. Parameterize into R of t. Then find R prime of t. Okay? So let's go ahead and start parameterizing this curve, right? Again, I want you to pay attention to the keyword here is a downward pointing normal, right? This again is not normal orientation. Okay? But it doesn't matter, right? We're still going to parameterize it using the normal way, right? For a circle, we always use the sine and cosine and sine parameterization method. So to get the equation of this pink circle, we're going to start with setting z equals to 0 equals to e of x squared plus y squared plus 36, right? I think everybody can agree that this is a number that's going to be that it's going to be a greater than 0 sort of quote unquote a constant, right? So we can divide both sides by e to the x. So we're just gonna get 0 equals to this equation, and then I think the result is pretty obvious right now, that x squared plus y squared equals to 36, right? To parameterize this circle, again, we're going to have r of t. Therefore, r of t is just going to be 6 cosine t, 6 sine of t, and then 0. All right, this is the standard way of parameterization, right? And then t belongs to 0 and 2 pi. Okay? Therefore, r prime of t will give us negative 6 sine t and then 6 cosine t, 0. Okay? And then step 3, we're going to parameterize the function vector field, right? Parameterize the function. Parameterize f of x, y, z into f of x, t, y, t, z, t, right? All right, for this problem, this is just going to be, right, f of the whole thing equals to, well, let's go ahead and start with just f, right? So f equals to y plus z cosine of x. Looks scary, right? Looks really scary, but let's keep going. Plus z sine of y I'll just call it Z7. Why I'm removing the parentheses for ease of readability. And then X, Y, E to the Z, right? So this is our vector field. I'm going to cut it and paste it. F equals to this thing, right? And then we're going to parameterize it. So F of xt, yt, zt, right? So what we mean by parameterization is just wherever we see a y, right, we're going to replace this with y of t, x of t, which is going to be right here, and then z of t. Okay, hopefully you see the brilliance of this question now, right? So what we're gonna end up with is just 6 cosine t plus 0, right? We substitute 0 into here, and we don't worry about the rest. And then we're going to have negative 6 sine, negative 6. Give me 1 second. Give me 1 second here. That this should be. Oh, never mind. This should be this of x of t, y of t, z of t should be right here instead of down there. I mislooked, right? So that's r of t, that's r prime of t. I made a small mistake right there. So 6 sine of t plus 0, and then minus 6 cosine of t plus 0, and then we're going to have 0, right? Because well, never mind. It's just 36 sine of t, and then cosine of t. Okay. All right. X of t, y of t, x times y is just 36 times cosine and sine. Okay. So now we can finally utilize the Stokes theorem, right? The Stokes theorem is defined as follows: as the surface integral of del cross f, and then times the normal vector dx equals to the line integral of the boundary curve, and then of f dot dr. Right, so this is not really a useful definition, so I'm gonna rewrite it as cf dr dt. Right, dr dt is just r prime, and then dt. Right, now we're gonna integrate with respect to t. So let's just go ahead and quickly compute this part right here. Okay, so this part. All right, so f dot d dr dt equals to this thing dotted with this thing, right? We already derived from there, derived these items before, and this just going to equal to negative 36 sine square of t, and then minus 36 cosine square of t equals to negative 36, right? So finally, we're going to have the integral f dr dt just gonna equals to negative 36, and then dt, our bounds will be 0 to 2 pi, and then so 0 to 2 pi, this will be negative 72 pi. Oh, but wait, remember, this is a downward pointing normal, right? So if you follow the right hand rule, right, if you align your 4 fingers on your right hand align with the curve, this is our normal parameterization method, you will see that your thumb is pointing upward in the positive z direction. So your normal pointing vector will be upwards instead of downwards. So in order to fix that, in order to follow the correct parameterization, we're going to have we're gonna flip the sign of the final integral, right? Since problem requires opposite or parameterization slash normal vector, right? Flip the sign of integral after following the normal parameterization. Okay? So the actual result will be negative 72 pi equals to 72 pi. And then this is the correct answer for question number 19. Right here. Question number 20. Compute the surface integral, which is the outward net flux of the vector field F across the surface S, which is the boundary of the solid bounded by z equals to 0, y equals to 0, y plus z equals to 2, and then z equals to 1 minus x squared. Okay, so again, I think many people would think that this is a surface integral in vector field, but in fact, this is a divergence theorem problem. And particularly is given surface integral, but compute the triple integral or volume integral. Okay? And then the key word here is, first of all, it's flux, right? So that tells you it's something of a surface integral, right? So this tells you this is a surface integral, problem, or at least related to surface integral, right? And then another key here is the difference between a divergence theorem problem and a regular surface integral problem is that oftentimes that the divergence theorem problem must have a closed surface, right? A closed surface. That means volume exists, right? Because the divergence theorem is a conversion between double integral and the triple integral, right? And the double integral is the surface, and the triple integral is the volume. So if we have an open surface, the volume simply does not exist. So there's no triple integral to compute, right? So we must have a closed surface. In this case, it is a closed surface. And then the key word here is also a solid, right? A solid, right? A solid, and also net outward flux. Okay. So to solve this type of problem, right? Again, we're going to determine whether the surface or volume integral is easier, okay? So in this case, the volume integral is much easier. Okay, so let me explain by that. So so for most of if not all divergence theorem problem, right, surface integral usually are there are multiple surfaces to an object. Maybe an exception will be a sphere. Maybe that will be a bit easier, but I would rather take a triple integral in the spherical coordinates rather than trying to parameterize crazy things to to parameterize that sphere surface. So what my point is that many times to compute the divergence theorem, there will be oftentimes you will require multiple surface integrals, right? Because a solid usually consists of more than one surfaces. So it's oftentimes a lot easier to just compute a volumetric integral because there's only one volume, but there could be multiple surfaces. Okay, and if you just happen to have the time, which I highly doubt you will on an exam, this is what the region looks like. Okay, so let me break it down a little bit for you. Right, so this region is z equals to 0, right? So this red thingy is bounded by the z equals to 0. So it's everything above the positive z axis, and then also it's bounded by the y equals 0 surface, right? So everything is in a positive z axis, and then this plane that you see right here, this plane that has dotted black line, that is z equals to y plus z equals to 2, right? So let me just make it line a bit thinner, right? This is y plus z equals to 2, and then this thing that looks like an arch, like a tunnel, that is the z equals to minus 1 minus x squared. Okay, so z equals to 1 minus x squared. So you can see that this cylinder is extending towards the y, extending towards the y side, but it's being intercepted by this surface of this plane, right? So it looks like a weird looking shape, and then this is my best attempt to draw this. It took me like 10 minutes to try my best to draw this thing accurately, but at least I hope you see what is going on here, that a cylinder is being intercepted by a slanted plane. So again, right, as we have discussed before, right, this object will have multiple surfaces, and they are hard to compute, very hard to compute, in fact. But there's again still one volume, right? So we in most cases for divergence theorem, we should stick to the volumetric integral. Okay, so now we know we're going to choose the volumetric integral of divergence theorem, and then second thing we're going to do is to find the divergence of f, right, which is, right, in this case, which will be we'll just take the partial derivative with respect to x. We get 1, we plus another 1, we plus another 1, so we will have 3, right? So then we're just going to take advantage of the property of divergence theorem, right? Step number 3, which is the divergence theorem, right? So surface integral of f dot n ds equal to triple integral of the region d and divergence of f dv. Okay, so this is actually the hardest part of the problem, is how do you set up this triple integral to solve your volumetric integral problem. Okay, so let's take a look at this this region. Let's say let's try to use set up with the standard way of dz, dy, dx, right? So the first thing that we need to face is, what is the z bounds? Well, if we set up in this way, that we have z equals 0 from the bottom, right? So 0 dz, but what is the top? right? What is the top, right? So before the cylinder and the plane intersected, the z-axis was bounded by the cylinder, but after that, after they're intercepted, the volume, the region is bounded by the plane, right? So so at least you have to set up two triple integrals to solve this problem, which isn't really convenient. I mean, technically you can do that, but it's just not convenient in my opinion. So what are we gonna do? How about we try the dy first? Okay, let's try with dy first, and then let's go with dy dz dx. Okay, so again we're gonna face the problem with 0, and then what's the upper region? Well, if you look along this direction, right, the upper surface is always bounded by the equation of the plane. Did you notice? Right, it's always bounded by the equation of the plane. So this will make our life a lot easier. So that's the order of integration we're going to choose. So dz dy dx, dy dz dx. So y1, right? So we're gonna set up y1 equals to 0, and then y2 equals to 2 minus z, right? We're going to rewrite y plus z equals to 2 to y equals to 2 minus z. Okay. And then again, so divergence will have the integrand will be of divergence of f, which is 3 right here. And then for y, we're just going for z, right? So let's go ahead and then draw the zx trace. So why do I draw the dx trace, you might ask? Because the most useful trace will contain the variable of the last two integration variable. Particularly, the middle one will be the intermediate variable, which will be used for the vertical axis, and then the outermost variable, which is x in this case, will be used for the horizontal variable. Okay, so we're going to use the zx trace. Okay, so, and it's just going to look like a parabola, right? So it's going to look like a parabola above the z-axis, right? Because z should always be greater than 0. So z equals to 1 minus x squared, and this is from 1 to negative 1. So we're going to have z1 equals to 0, right? The lower bound of z, right? Z equals to 0, this line, and then the upper bound is always bounded by this parabola, right? So it's 1 z2 equals to 1 minus x squared, and then finally we're going to have negative 1 to 1, right? So the left bound is a constant, right bound is a constant. So what we're going to get is negative 1 to 1, 0, 1 minus x squared, right? So 3 times 2 minus z dz dx. We're going to end up having negative 1 to 1, right? So we're just going to go ahead and integrate this really quickly. So 6 minus 3 over 2 z squared, and then 0 from 1 minus x squared dx equals to negative 1 to 1, 6, 1 minus x squared, and then minus 3 over 2, 1 minus x squared dx. And then we're going to break this whole thing apart, which is where we will have minus 1 to 1, 6 minus 6x squared minus 3 over 2 plus 3x squared, and then minus 3 over 2 x to the fourth dx equal to negative 1 to 1, 9 over 2, negative 3x squared minus 3 over 2x to the fourth dx. Okay, so this is just all algebra and then basic calculus, and then we're going to end up having 9/2x minus x cubed minus 3/10 x5 from -1 to 1, which we will have. We're gonna evaluate this component by component. So we're going to have 9/2 minus -9/2, right? For this part, we evaluated from -1 to 1, and then we're turning our attention to this case, which is -1 minus -1, and then we're going to have -3/10. Again, the same case with 1 minus -1, and then we are going to end up having 9 minus 2 minus 3/5, which will give us 35/5 minus 3/5, and then equals to 32/5. And this is the correct answer for question number 20. And that concludes the MA 261 Fall 2019 final exam walkthrough. And thank you everybody for watching, and have a good rest of your semester, and the best of luck to your final exam.